Hello everybody. In today's class, we shall discuss error detection and correction code. In the last class, we saw unweighted code and we continue with the discussion of codes which are not weighted, and here we shall see the code word that is generated is useful for detecting any error in the bit position, and if possible correction will be done for some specific kind of coding. So, we shall discuss Hamming distance, and while discussing it we also shall include discussion on parity code that we have seen before, even parity and odd parity, and then we shall look at a specific code called Hamming code, its generation and how it is used for 1-bit error correction and 2-bit error detection. So, first we look at what is Hamming distance. So, Hamming distance is the number of bit positions by which code words differ from one another. Okay. If there is one code word and there is another code word, we look at the bit positions where they differ, and how we can get it? We can take bitwise XOR operation of it. Okay. So, whenever the bits are of same value, I mean code words is particular position. So, if it is 1 1 or 0 0, XOR gate output will be 0, and when they differ, that is 1 0 or 0 1, the output will be 1. So, these XOR bank of XOR gates, you look at its output and see how many places it is 1. So, if those ones we count, then that will give us the distance between two words. Okay, two code words. Okay. So, that is what we say as Hamming distance. Okay. So, to any group of binary digits and another digit, this is the way we can calculate the distance. Okay. So, we have seen parity coding. So, let us look at an example of even parity coding, and there we look at two data. One is some random data we are talking about. Okay. Later we shall look at some specific data to find out some minimum distance or so. Okay. So, this has got 1 2 3 4 4 1. So, even parity we are looking at. So, the parity bit that is getting generated will be 0. Ultimately, all the bits including the parity bit will be even. So, that is the objective, right. And another data is this. So, it has got 5 1. So, the parity bit is 1, okay, after XORing, right. So, we refer to that discussion on parity code, where XOR gates were used for generation and detection of parity bit, parity code related error in the transmission reception. Okay. So, eventually we have got 6 ones over here. So, if we look at bitwise XORing of these two, so we shall see that here is 1 1, 4 ones are here, another one. So, 6 ones are there. So, we will say between these two the distance is 6. Okay. So, that is how we calculate the distance, Hamming distance between these two code words. Okay. But for even parity code, so if we look at another case, say where the original data is differing only in 1 bit position. So, this is one case, all zeros, right, and just 1 bit is changing. So, it has become 1, right. So, what will be the corresponding code word? Here all zeros. So, that means the parity bit will be 0 and 1 1. So, parity bit becomes 1. So, that even number of ones is there finally, including the parity bit, right. So, now this is the minimal distance between to start with. Now, when we do the XORing and accumulate, we see that 2 ones are there. So, this is 2. So, for this kind of parity coding, where 1 bit parity code is introduced, we shall see the minimum distance is of 2, right. So, that is what we take note of. Now, the rule says to detect B bit errors, number of bits if B, then the minimum Hamming distance required is B plus 1 in the code words. Okay. So, we take the code words generated for detecting this error. Okay. So, error detection code. So, the minimum distance required is b plus 1. So, Hamming distance for this parity coding, the kind of parity coding we have seen before, is 2, minimum Hamming distance 2. So, we can correct we can detect rather 1 bit error. Okay. And for correcting b bit errors, what is the minimum Hamming distance required? The rule says it is 2b plus 1, right. So, to correct even 1 bit error, we need the Hamming distance 2 into 1 plus 1, so 3, right. So, with this kind of coding, we can detect 1 bit error, but we cannot correct any, right. So, this is what we have seen in the past on a error detection code using parity, introducing a parity bit. Okay. Here we have taken the example of even parity, it will stand good for odd parity also, right. Now, we look at another kind of coding called Hamming code, where we shall see how to correct a bit error as well. Not only detection is what we have seen as an example in parity code. Okay. So, Hamming code is something where we are putting not one parity bit, more than one parity bit, okay, at specific position. So, what are those specific positions? These are 2 to the power ith position. So, what are the 2 to the power ith position? So, 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8. So, these are meant by 2 to the power ith position. Okay. So, if we have a total code word that includes these parity bits, okay, which are included for the coding purpose, and the data which contains the information or the message or the numeric value, whatever, right. So, if we include all of them together, then whatever code word is formed, the 2 to the power 0, that is 1, so that is first position, 2 to the power 1 2, 2 to the power 2 4, okay, then 2 to the power 3 8. So, these positions will be filled by parity bit, okay, and the rest of the position will be filled by the data, like third position, fifth position, sixth position, seventh position. Okay. So, this is the way count will progress. So, with P1, P2, P4, these 3 parity bits we can go up to D7, right. That means, total code word will be 7, 4 data bit and 3 parity bit will be required in this kind of coding. So, whenever we go beyond that, we have to introduce a parity bit over here P8. So, with that we can go up to D15, and here whenever 16th position comes, right, we have to introduce a parity bit P16, and then again D17, D18 will continue. So, this is the way things are done in this kind of coding. Is it clear? Okay. So, with this we can understand that with m parity bits, m greater than equal to 2, the number of bits that we can code, message bits or data bit is n, then 2 to the power m need to be greater than m plus n. Okay. So, that is what we can see. Here 4 parity bits are there, P1, P2, P4, P8. So, m is 4. So, 2 to the power 4 is 16, right, 16. It need to be greater than m, which is 4, okay, plus n. So, here n we can go up to data, we can go up to 11, right. So, 15. So, you see up to 15, because at 16th position again another parity bit will come. So, this is what we can see over here. Is it clear how we are introducing the parity bits in the code word Hamming code? Fine. Now, so we know the position of the parity bit, right. Now, how we generate the parity bit? So, the values will be zeros and ones. Okay. So, what will be those zeros and ones? Of course, it will depend on the data, right. So, how it is generated? So, to generate parity bit for a system which is called Hamming 7/4 code. That means total length is 7 and number of data is 4, D3, D5, D6, D7, and number of parity bits are 3, P1, P2 and P4. Okay. So, we take this example. So, what we do first, each of these position 1 to 7 we are coding in binary, right. So, 1 its binary coding is 0001, 2 binary coding is 0010, right. So, this way we will continue, 7 is 0111. So, to generate P1, we shall consider all the positions, okay, of the data where the units in the units place there is a 1. Is it fine? So, D3, D5, D7, okay. So, these are the places we have a 1 in the units place. So, P1 will be generated by XORing these bits, whatever these bits, whatever message you are having. So, these are the places, whatever the bits are there, we XOR all of them together and then we get P1. So, how to get P2? P2 will be obtained by looking at ones that are present in the 2's place. So, this is all P2 will be generated. So, it is not coming. So, D3, right, then D6 and D7. They have got 1 in the 2's place. So, D3, D6, D7, you can see that. And how P4 will be generated? Now, you can understand, you can extend the idea. So, we shall look at ones present in the 4's place, right. So, 4's place 1 present here in D5, then D6 and D7. So, that is what you can see. Is it okay? So, if you extend it, you can see, for example, if you are having total code word is code length is 12, code word length is 12, right, and P1, P2, P4, P8. So, 4 parity bits are there and then 8 data bits are there. So, if you want to code it, okay, then the parity bits need to be generated. So, P1, again we will look at places where there is 1 in the units place. So, P1 we are generating. So, D3, D5, D7, D9, D11, this is there, right. Similarly, P2 will look at places where there are 2, right. So, D3, D6, D7 already there. You can see that D10, okay, and D11, these 2, they join in P2 generation when there are 12 bits, 12-bit code word. So, P4, D5, D6, D7 was already there, D5, D6, D7 up to this. Then in 4's place, you can see over here that D12 has got a 1, okay. So, D12 will come. And finally, for P8 in the 8's place where there is 1. So, P8, D9, D10, D11 and D12, okay. Is it clear now? Now, you can see if you put various numbers and all. So, the minimum distance that you can get over here is 3 between 2 code words, and for which it can detect, as I said, it was B plus 1. So, B will be 2 and can correct, it was 2B plus 1. So, this is 1. So, this is what it can do, okay. And of course, what you can understand by doing this, we are actually increasing the length of the message, right, length of the data. So, actually out of which useful data is 8, 8 is something which is unknown and P is the one that you are introducing. So, at the other end, so 8 out of 12 will be useful in this kind of coding, and in the 7/4 code 4 data bit out of 7 will be useful. So, this is the way one can actually define the rate at which actually information is going from one place to another. So, because of the introduction of this parity bit, you can see actual rate, though you are sending 7 bits, but your message conveying bit is only 4. So, rate has been reduced. So, this is one thing that we need to take into account, that when we are doing it, Okay, to get some benefit out of this kind of methodology, there is some cost associated. This cost is additional bits that need to be sent along with, which will bring down effective data rate, effective transmission rate. Okay, fine. Now let us look at an example. Okay, so in this case the data is 1011 and 0101. So basically 8 data bits are there. So 4 parity bits will be required. So data bits are placed D3, D5, D6, D7, okay, D9, D10, D11, D12, right. So this is the way they are defined. So this is D3, D5 up to this is D12. Rest are your, so we note that the nomenclature how these they are designated. So to get P1, okay, so D3, D5, D6, D7, this is D9, D10, D11 and this is D12. So D3, D5, D7, D9, D11, this you need to take. So D3 is 1, D5 is 0, D7 is 1, right, D9 is 0 and D11 is 0, right. This is the way we look at it. XORing means we shall look at the number of ones. So if the number of ones are even, okay, the output will be 0. If the number of ones, total number of ones are odd, then the output will be 1. So number of ones are even in this particular XORing. So the output here is 0. Is it clear? Similarly for P2, D3, D6, D7, so we can substitute all those values. We can see that this is 0. P4, similarly we can see here there are 3 ones, D5, D6, D7, D12. So D5 is 0 over here, D6, D7, D6, D7 are 1, 1, 1, 1 and D12, D12 is 1. Okay, so 3 ones are there. So the output is 1. And finally, P8, you can say that this is 0, right. So then the coded data will look like this, 0, 0, because P1 is 0, P2 is 0, P4 is 1, so P4 is coming over here, D3 is 1, so D3 is there. So the one that are in bold is the parity bit. Okay. So this is the way the coded data will be generated and it will be sent. Okay. Now let us see how the correction, so called 1-bit error correction, that is possible through this Hamming code. Okay. So if we just look at the way it is generated, so for example if we consider that in this particular case D7 bit is received erroneously. Okay, just for example, actual example we shall see later. So D7 bit is received erroneously. So whatever was there, it has been flipped. Okay. So what we do in the receiver side, other than what was required to generate the parity bits, D3, D5, D7, D9, the ones position, with them we also XOR the P1. Is it okay? So if all these were odd, D3 to D11, then P1 would have been 1. I mean the number of ones there, if that was odd. So together it would have been even. Is it clear? So if we include P1 in the XORing process, the way we had done for single bit parity code, okay. So inclusion of P1 in the receiving side in the XOR operation would have made everything even, the whole of it is even. So if D7 was not erroneous, then this XOR operation together with P1 would give me 0. So if all of them together was 0, then P1 would have been 0, which is the case in a specific example. Or if it was 1, it was. So effectively all of them becomes even parity, right. So D7, if not erroneous, this C1 generated will be 0. But if D7 is erroneous, it will generate because of it has flipped. So so odd number of 1 will come there. So C1 will become 1, right. D7, let us see what else, which other area where it is there. So, D7 is over here again, D7 is over here again, and it is not there with C8, right. So, D7 flipping will not affect C8, right. So, if you now put them together, I mean if you take the receiving side, so what will it generate? C8, C4, C2, C1, it will generate 0, 1, 1, 1 from this side to this side, and this refers to 7th, 0, 1, 1 is 7, okay. So, that indicates that 7th bit is erroneously received, and if you invert it, you will get the actual information, right. So, this is how 1 bit error correction is done. So, it will be true for any other bit position. So, you will see that only corresponding place over here is getting flipped, getting a 1 because of the flipping over here, okay. So, the example that we have taken, the code word, right, we consider for a change, not say D7, D7 is already understood, that 11th position the bit has changed, bit has flipped. So, this 0 has become 1, right. So, we shall then perform with the parity bit that is there, wherever D11 is present, D11 is present, D11 is present here, right. So, the D11 is present here, okay, and D11 is present here. So, these were the places which was 0 before in the generation process. Now, this has become 1 and parity bit got added, okay. So, it is not there with this one, D11 is not there. Now, if you do the XORing operation, you can see 1, 1, 1, 3 ones are there. So, output will be 1. This is your P2, this is your P4, right. This is your P1, this is P2, this is P4 and this is P8, okay. So, this is 1, this is 1. In this case 4 ones, because of presence of this P4, these 3 ones, finally it becomes 0, and because of these 3 ones are there, this is 1. So, what we get? 1, 0, 1, 1, C8 to C8, C4, C2, C1. So, this is what we are getting. So, this indicates 11 in decimal. So, 11th position there is error, and if you flip it, you can get the corrected bit word, okay. And note that the flipping can occur even in the parity bit position, because when the message is coming, you do not know because of the noise or some issue which bit position is. It is not necessarily only the data bits will get corrupted, okay. So, if say any of the parity bit is getting corrupted, say P4 is getting corrupted, okay. So, P4 is getting corrupted means P4 is there in the, let us consider that P8 is getting corrupted. So, P8 is there with this one, only this particular case P8 is not there in any other places. So, only because of it has changed, it should have been even parity whole of this thing. So, this output would have been 0. Now, this output will be showing 1 C8, and since P8 is not there with any one of them, right. So, all of them will be showing 0 because they are not getting affected, all those bits are in order. So, 1 0 0 0 is that what we will get, and the final you can say that 8th position is erroneous, okay. Is it clear? So, if it is 8th position, then P8 is erroneous, okay, P8 is erroneous. Now, let us look at 2-bit error detection that is possible here, okay. So, let us see what does it mean. So, we consider a case where this D7 is erroneous and D5 is also erroneous, okay. So, what will happen in this case? C1, since 2 bits have flipped, so C1 will be 0 only, right. If one bit flips, then it will give a 1 when we consider the parity bit and all, overall it is even parity. Since 2 bit has been flipped, so it will be giving you 0. So, you cannot detect any error over there. Okay. So, here D5 is not there, so D7. So, in this case this will give a 1 because only one bit has flipped. D5 D7 is there in C4. So, 2 bits have flipped, so it will not detect any error, and C8 does not have D5 or D7. So, it will not detect anything. So, only C2 will give you a indication that there is a error, but it is not, it cannot correct it because it is indicating 2. Okay, if only one bit error was there, right, 2, then you could have seen that it is P2 that has been erroneous. Okay. So, but that is not the case here. So, more than one bit correction is not possible. So, D5 D7 cannot be corrected, right. So, similarly D3 and D5 if you see, so D3 D5 both flipped, so that means this will be 0, it cannot detect anything, so 0, and D3 is here, D5 is not present, D5 is here, D3 is not present. So, they will generate 1 1, and your in this C8 case, neither of D3 or D5 are there. So, this will be 0. Okay. So, this again because of C2, C8 to C1 is not all 0. So, error is detected. Okay. Error is detected. Okay. So, if there are 2 bits erroneous, definitely we can see that it will be detected. So, the final C8 to C1 will not be all 0, right. Now, more than 2 bits flipping, let us see 3 bits case. Okay. So, we take an example where D3, D5, D7 they have flipped, okay, which is possible. This is one random case, right. So, C1 3 has changed, right. So, for which then if 2, then 1 cancels other. So, basically 2, so here then it will detect a odd parity, not even parity. So, this will be 1, right. The other case D3 and D7, so it will detect both of them is flipped. So, no error will be detected. Similarly, no error will be detected, and in this case D3, D5, D7 are not there. So, 000 1. So, error is detected. So, 3 bit error is detected. Okay. But we were saying that it can detect 2 bit error. So, 2 bit error detection is guaranteed. 3 bit error in this case got detected. Okay. But let us see another example whether it is getting detected or not. So, D3, D5 and D6. Let us consider that these 3 bits have got corrupted, have got flipped. Okay. So, D3, D5 is there in C1 generation. So, since 2 bits have got flipped, so it will not be detecting, it will be 0. D3, D6 is over here, 2 bits got flipped, it will be 0. D5, D6 is over here, 2 bits got flipped, so it will be 0. And in this case, none of the D3, D5, D6 are there, so it will be generating 0. So, 3 bits are erroneous, but the output is 0. So, it will be seen as that no bits, no error is there in the code word. Okay. So, that is why we are saying that it can detect 2 bit error and can correct 1 bit. So, this is the basic premise of error detection and error correction, and with Hamming distance and the relation between Hamming distance and the number of bits it can detect and number of bits it can correct. Okay. And there are many other options available. So, the idea here was to give you an idea foundation and how digital circuits can be made around it, and we have seen that these XOR gates, XOR relations are useful in this. So, to conclude, we can see that the number of bit positions by which code words differ is called Hamming distance, and Hamming distance is related to number of bits it can detect as erroneous, or number of bit it can correct as erroneous, erroneous bit it can correct. Okay. And in Hamming code generation, 2 to the power ith position you need to be need to have parity, and XOR operation is there for generating the parity bit, as well as looking at the receiver side and from that we can arrive at for the correction which position, and for detection whether there is a error or not. Okay. Thank you.